So welcome back everyone. This is the first video that covers the material of chapter 3 of the Advanced SQL course. But first things first, it's May the 4th today, so it's Star Wars Day. And May the 4th be with you always. Enjoy Star Wars Day and dive deep into the galaxy far away if you find the time. I'll certainly do that tonight. All right, so before we can do that, let's turn back to our discussion of Advanced SQL. And in chapter 3, we will cover data types in depth. So we had our playground table prepared for the discussion in chapter 1 and chapter 2, and that playground table of course had table cells, and we had like integers and boolean and text stored in there. That's okay, that would be considered standard data types, I would say, but there's a whole more to data types in SQL based database system, and certainly in PostgreSQL. So this is where it becomes somewhat system dependent, because every database system prepares and supplies its own set of standard and non-standard data types, and there is really more to integers and boolean and text when it comes to stuff that we can store in table cells. And this is the topic of this chapter, and we will explore this to some depth here. And there are some quite unexpected things that we can store in table cells, I would say. All right, so let's see. First, as I told you, there is more to types in table cells than just booleans and text and numeric types. And if we query the PostgreSQL meta level, so the system catalog, the table that Postgres maintains to organize itself, then of course we can also discover information about the available types there. And this is exactly what the PG type catalog table can tell you. If you issue this particular SQL query against the system catalog of PostgreSQL, then you will get information about the available types inside the system. And if we disregard particular array element types and disregard composite types, record types, and only look at the atomic types that can really be held in one table cell, then you would probably get a listing like this. Let's switch over to the real system and see what really is in store regarding types in PostgreSQL. So here we go again with our interactive setup, and this is the variant of the query that you've just seen on the slides. So query the catalog schema table, disregard array element types. So we are really looking for real types here, not in connection with any array types. And arrays will be the topic of the next chapter. They deserve a special discussion. All right. We will only list scalar atomic types and not record or composite types. And if we do that, and even if we disregard these types of types, then you still see that PostgreSQL lists more than 100 types. Let's scroll to the beginning here. More than 100 available types to us. This is stuff that we could store inside the table cell of PostgreSQL table. So of course booleans, and then something called byte A or byte array, and character and integer data types. Regproc, I don't know what that means. Well, I know, but this is not important here. It's a registered procedure. It's text. It's typical various types of IDs, JSON and XML data, and the list goes on. Polygons, circled, looks like geometric stuff is in there. Money, okay. Different types of numeric types. We have special types that are suited to store networking information like DNS addresses, IP addresses, and so on. Different data types for character strings and time stamping. We will talk about these. The list goes on and on and on. It's really a rich collection of data types that are available to you, normally much richer than your normal programming language would be able to provide. All right. There's one construct in the SQL language, the so-called typecast, that you may also know from your favorite programming language. Convert a value of one type, tau, to a value of another type, tau prime, if that's possible at all. In SQL, such typecasts normally happen at runtime. So casting really involves runtime effort and has some runtime impact. Really fine-tuning queries really has to take care the effort spent and the time spent in casting a value from one type to another, and careful tuning will try to avoid such casts. But this is a topic for a different day. For efficiency, here we're looking at the SQL construct that is available to us to cast stuff. So there's different syntactic forms that you could use in PostgreSQL to perform casting, to express casting. All of these are equivalent. The first would be considered the SQL standard. So given an expression E and such the value that is associated with E, if we evaluate this expression, we get a value. Try to cast the value into type tau, if this is possible at all. All right. This would be the SQL standard syntax. The same will happen with this particular syntax, with the double colon here. And if you've ever used a functional programming language like Haskell, then you will recognize this particular notation or syntax here. It has been borrowed from there. It means the same. And this is yet another syntax. It's like a constructor syntax, type in front and then the value after the type. This looks like constructor syntax in many object-oriented programming languages, for example. Okay, such typecasts may of course fail at runtime. So casting such values may be impossible. And because many of these, if they cannot be statically evaluated, will happen at runtime, these are a source of runtime errors in your SQL queries. So be aware of that. And we will see some examples of that, of course. This is quite a verbose notation, especially the SQL standard one. And because this is the case, SQL will perform implicit casts for you whenever it can do that, whenever these are required. So if SQL knows about tau, the target type that we should cast to, then SQL can perform such an implicit cast for you automatically and thus make the syntax more compact and more readable. So this is, for example, the case if we perform insertions into a table. Insertions into a table will insert into a typed table. So the columns A, B, C, D have been assigned column types when we created table T. So if we insert this particular row of 4 fields, then for each of the fields, it's known which type they are supposed to be. In our playground table, if we recall, column A was of type int, and this was text, this was boolean, and this was int again. Okay, so if we specify this particular row, then SQL knows the desired target types and will perform implicit casts for us. This 6.2 is a numeric value, it's not an int, but it will be casted to int, and that cast will go just well. And I will show you in a minute in the interactive prompt. Okay, this null value is supposed to be a text value, and it will be casted implicitly to a text value by SQL because it's known that the second field in the rows of a T table have to be of type text. This is a textual true value, so consisting of characters T, R, U, E, and it will be successfully casted into a Boolean value as required by column C. This is a textual representation of an integer, and it will be casted to an integer automatically for us. And that will also succeed because this is an accepted representation of an integer. So let's see, let's switch over to the editor again, and let's get table T back into place. There we go. Okay, table T as we knew it. Table T. All right, there it is. Okay, so we can play with that in a minute. So let's first see how typecasting works. So that would be one particular syntax for typecasting using the FP-inspired syntax, and it probably does what you expect. If 6.2, the floating point value, is casted to an integer value, then we get 6. If 6.6 is casted into an integer value, we get 7. So some rounding is going on here. All right, let's do that. And yes, that's what we see. All right. This is the other possible syntax where you use a constructor-like syntax. So type in front and the value, the expression to be casted in parentheses behind. All right, so this is the textual representation of a value and we want to cast it into a date value. Okay, haven't used the date type yet much, but you can expect, you can imagine what this is supposed to do. And this is today's date. It's Star Wars Day, as I told you. And this should be a valid representation, string representation of current date. And that should work too, I guess. So let's mark this and evaluate. And yes, it works. And it gives us the date value. This is the internal representation of the date value. You see year in front, then month, then day. But we will come back to this. All right, so these are explicit casts. So the types have been given explicitly here, like here or here. Okay, but implicit casting is going on in SQL, as I told you, and the example from the slides, well, it was inserting this row in which for all of the 4 fields casting has to go on. So let's try that row. Works fine. So insert 01, nothing has been rejected, 1 row has been accepted, casting must have gone on here. So let's see how table T looks now. Okay, so there's indeed a new row that has been inserted, a proper boolean has been created, a proper integer has been created through casting. This is a null value, obviously that one that fits into the text column, so casting went just fine. So as you can see, there's obviously facilities inside PostgreSQL that are prepared to convert all kinds of textual representations, of values of different types from the textual string representation into the target type. We can represent booleans as strings. We can represent integers or numeric types as strings, switching over again. We can represent date values as strings, and if these strings are well formed regarding the target type, in this case date, then some pretty sophisticated casting can go on here. Okay, so let's look at this a bit more closely. It's a particular literal syntax, a syntax for literals or constant values that is supported by SQL, and these literals are simply specified as textual strings in single quotes. All right. So what we are talking about is really casts from the text data type, to other target data types. And support for that is really extensive in SQL and in PostgreSQL in particular. So literals in text syntax are casted using, of course, the standard syntax rules that we've already been introducing. So the SQL standard syntax or this FP inspired syntax. All right. And this will succeed if the value in quotes has a valid interpretation at this target type tau. All right. And this is SQL's way to really embed complex literals of a myriad of types inside SQL sources. So dates and times, we've already seen that they have a natural string representation, but more complex values and their types like JSON or XML or different geometric objects, they all have possible literal representations as text. And PostgreSQL and SQL will do its best to perform the desired casting from these literal textual representations to target data types. This is really vital. If we import data from textual representations, for example, CSV files, comma separated files, which are just plain text files, into our type tables. There must be a component in the system that performs casting, in this case even implicit casting from textual, say, CSV file representation, textual representations into the type tables that we're using inside PostgreSQL. Okay, so let's see how this works in practice. So let's look at this example. And This is an example that works over a literal 2-column table. You see these 2 columns in each of the 6 rows here. Okay. The first entry in all of these columns are different possible textual representations of true Boolean values. And associated false representations would be here in the second column. And a variety of these is shown here. True and false would be the vanilla forms. True and false capitalized in any form would be okay too. Actually, any prefix of the true or false words here would work as well. So T and F are valid textual representations of the true and false values. 1 and 0 would be 2, yes and no, on and off. All of these would be valid representations of Boolean values. And we can prove that by just iterating over all these 6 rows, 2 columns each. They have a yup and a nope column here. All right, I can see that. And here in the select clause, we perform the cast to Boolean, an explicit cast to Boolean, and ask the system to interpret all of these textual representations of Booleans as real Booleans, and let's see what comes out of that. Okay, there you go. It's the yup and nope columns, and we have 6 entries there. They're all true and all false. So really a very extensive library of casts from text representations into Boolean values. And all of you have seen CSV files, or maybe the Excel sheets that lead to these CSV files that have representations for Booleans like yes, no, on, off, 1, 0. PostgreSQL will be fine with these. No conversion or no rewriting before ingesting or importing into PostgreSQL necessary. PostgreSQL is really flexible in this case. All right. So let's see if this also works with data types that are more complex than Booleans. For example, the XML, the Extended Markup Language. A language that provides a textual syntax to represent ordered, really complex structured ordered trees. And you all know the typical open and close tag syntax of XML. And I've brought one of these textual representations of an XML document with me, and I could use PostgreSQL's textual representation on casting from text into a target data type, in this case into PostgreSQL XML data type, and have this textual representation automatically be converted into a valid XML document, if this is possible at all. If this is regarding syntax, a valid snippet of XML, and it is in this particular case. You see that the snippet itself contains quotes. Here is the attribute value 42 is quoted here, and now you probably expect all kinds of nasty quoting and escape quoting and so on going on here. But PostgreSQL is also very flexible regarding the quotes that we can use to include the literal text in. So normally we would use single quotes, but if these single quotes are of importance inside the textual literal itself, then we can use this particular form, these double dollar signs on either side of the textual value to be quoted, and use these as the markers, the borders for the textual value that we try to embed. So these would be valid replacements. The double dollar signs would be valid replacement for the quotes. All right. Actually, the syntax is even more flexible. I could just use this, for example. So insert a particular ID between the double dollar signs here if I only use the same ID in the beginning at the end of the quoting. So in the starting and the ending quotes. So let's not do that here. We could do that. So quite some flexible design of the quoting here. Okay, so let's try that. Is this valid XML? Okay, so the quoting went well. What we see here looks like the original text, but it's not text anymore. It has been quoted to XML, and internally it now has a tree structure that we could exploit to navigate the XML document, to use, for example, XPath to look inside the XML document and so on. All of this is possible now. Okay, so let's see whether this funny syntax using the dollar signs. So let's quote a number here, the 42, using the strange quoting, and that should work as well. Okay. So to prove that there is really some parsing and some understanding going on, that this is not just a literal copying of this text string, that really XML parsing is going on, let's provide an XML document XML snippet that is syntactically not valid. As you can see, there is an opening R tag inside this snippet, but there is no closing tag. All right, so opening tag without closing tag, this is not well-formed XML and should be rejected. And if this cast does anything regarding XML parsing, it should fail now. So let's see whether this fails. All right, so we get an error message, an opening and ending tag mismatch. So the R open tag has been closed by a T closing tag. This is indeed not matching. So this is a valid XML parsing error message. All right, the chunk is not well balanced. This is the chunk, the text to chunk of XML. It's not well balanced regarding its opening closing tags and has to be rejected. All right, and now for a final example, let's look at the importing of CSV files, as I mentioned before. This would be one of the major ways to ingest data from external applications, spreadsheet for example, into PostgreSQL for further processing. So let's just recreate our playground table T in this particular case. So let's just get rid of everything that has been in T. All the 6 rows are gone now. All right. So and now let's copy these CSV representations of the 5 original playground rows. Let's copy them back into table T. There's a particular copy command to do that. Copy the contents of this table from what I give you here from standard in. All right, from the standard input. The standard input can be a part of the SQL script that we're currently working with here itself. All right, so this is the input that should be converted to match the rows of T and then inserted into table T. All right. To supply the system's information about which format has to expect that's coming in from standard in, we provide this information here. So the format will be in the CSV format, so comma separated values. There's a special representation, our favorite representation of the null value, this little square symbol. This is all we need to have PostgreSQL start successfully parsing these 5 lines until it finds this particular end of file, end of standard input symbol. All right, and all of these values are of course textual values, just a CSV text file snippet. And implicit casting from textual values from these 3 0, which together make up a valid representation of 30, or these TRUE, which make a textual representation that's valid for a Boolean. Automatic implicit casting is going on to convert all of this textual information into typed information that can fit into table T. Okay, 5 copy rows, table T. There it is again. We have recreated from textual values through implicit casting. All right, so this is a first glance at the extensive data type support in PostgreSQL and the extensive support to enclose literal values of different types, be it Booleans or be it XML documents, that can then be casted to their typed representations if they are valid. All right, and we will make plenty of use of these features, as you can imagine, because we want to ingest all sorts of cool types into our tables. So let's do that in the upcoming videos. For now, I'm saying goodbye and see you soon.